about models of the atom from a historical perspective. Really early theories. 400 BC, Democritus thought matter could not be divided indefinitely. Basically, he pounded up materials in his pestle and mortar until he had reduced them to the smallest possible particles he could, and he called them atoma, or atoma, which is Greek for indivisible. And from that, he thought that you could not just keep going forever, that at some point matter would be as broken down as it possibly could be. Now, as we're going through this, I may go a little bit quicker than you're quite ready for. Don't worry about it. It will get put on the web page. Okay, a little bit later, you had Aristotle come by, and he was a big proponent that science basically was what you did in your head. In other words, it was about philosophy and thought and argumentation as opposed to experiments and evidence. He modified that idea about matter to be basically there were four elements: earth, fire, air, and water. He was wrong, but he was such an influential person that his theory persisted for thousands of years. And so sometimes when science talks about not wanting to appeal to authority, this is exactly the kind of thing. Somebody could be so famous and so important, and yet they can still be totally wrong. So we always want to go back to the evidence. So a little bit more recent now. We're going to start with John Dalton. And basically he proposed a modern, and we call it modern because 1800s, modern atomic model. And he said this has to be based on experimentation and not just reason. And he had a few ideas for his theory. First off, he thought that all matter is composed of extremely small particles called atoms. So notice that he's gone back to that original idea about matter. He thought that atoms of a given element are identical in size, mass, and other properties. So, for example, all carbon atoms would be exactly the same. All hydrogen atoms would be exactly the same. He thought atoms could not be subdivided, and he did not think they could be created or destroyed. They were just part of the natural universe. He also thought that atoms of different elements combine in simple whole number ratios to form chemical compounds. For example, H2O, 2 hydrogens and 1 oxygen. That would be whole number ratios for that compound. Or CO2, 1 carbon and 2 oxygens in that case. And then basically he felt that from his experiments that in chemical reactions, atoms are combined, they can be separated, and they can be rearranged. So this kind of goes back to they're not created or destroyed, they're basically just rearranged from, shall we say, one combination to another combination through the process of a chemical reaction. Now, early 1800s, technology is not that far along. Some of these things weren't quite right. Obviously, atoms have smaller pieces than just the atom itself. However, there was a lot here that was quite revolutionary. Now, his ideas accounted for a couple of, shall we say, laws that we still use today. First is the law of conservation of mass. Whether you're talking about atoms, mass, matter, energy, basically the idea is the same. We don't create it, we don't destroy it, we just transform it from one form to another form. So it's always there in some form. Basically everything that we might possibly do or that we might observe in nature is basically just transforming it, rearranging it. So matter cannot be created or destroyed. He also believed in the law of definite proportions. Compounds are composed of atoms in fixed, simple whole number ratios. H2O, an example, again, 2 hydrogens to 1 oxygen. So, no matter how much water you had, if you were to look at all the hydrogen atoms and all the oxygen atoms, it would still come out to 2 to 1. Same thing for, salt, NaCl. It would be 1 to 1 ratio, whether you had a little bit or had a lot. It was always going to be in these fixed, simple whole number ratios. And then he also, very similar law of multiple proportions. This is more directly with the masses as opposed to the actual atoms themselves. The masses of the elements are combined in simple whole number ratios. So again, if you look at something like H2O, 2 hydrogens, 1 oxygen, but now instead of focusing on the atoms, if we focus on their masses, we have 2 hydrogens, so that's a mass of 2 grams, if you will. And the oxygen is 16. 16 divided by 2 is 8 to 1. So basically, if you were to take an amount of water, and it really doesn't matter whether it's liquid water or solid water or vapor water, you're always going to have that mass ratio of oxygen to hydrogen of 8 to 1. Okay, now if it's a different compound, like say CO2, the entire molecule, you've got 12 for the carbon, 32 for the oxygen, because you have 2 of them. And if you worked out the percentages, you would find the percentage of carbon and the percentage of oxygen would remain fixed no matter how much of the stuff that you had. So very similar law of definite proportions and the law of multiple proportions. One deals with the number of atoms themselves, and the other deals with their masses. Now, like I said, he came a long way, but there were some problems with what he had. He didn't quite define everything. So then we have Thomson, who came along, and basically he's the one who figured out, hey, we got electrons. So atom wasn't the smallest thing. Atoms have electrons, these negatively charged particles. Basically what they did is their experiments used cathode ray tubes. It's basically a tube that has a vacuum inside. They have a current with it, and they found that the surface of the tube directly opposite the cathode glowed. They hypothesized the glow was caused by a stream of particles, which they called cathode rays. So initially, if you will, an electrical current or electrons were called cathode rays because related to the experiment where they were found in cathode ray tubes. Basically, what they found was the cathode rays were deflected by a magnetic field in the same manner as a wire carrying electric current. And they knew from other experiments that the wire carrying the electric current was known to have a negative charge, so they figured out the cathode rays must have a negative charge as well. Basically, the rays were deflected away from a negatively charged object. And you will find that this is true. Opposites attract, but like charges repel, so negative charges repel other negative charges, positive charges repel other positive charges. So as I said, a lot of this experimentation with the cathode ray tubes, and they figured out, hey, we got these negatively charged particles, which we initially called cathode rays, but then became known as electrons. So there's a picture of a cathode ray tube, and it's hooked up basically to a battery or a voltage source. You have a gas inside the tube. You can see the cathode ray. And one of the things they found out was, hey, the ratio of the charge of the cathode ray particles to their mass was always the same, regardless of the metal used. So in other words, they found something that was kind of fundamental. It didn't have anything to do with what element they were investigating. This ratio came out the same. So here was going to be a particle that was a part of all elements. And so this was his basic idea. Hey, we got an atom which is made up of scattered electrons unevenly within an elastic sphere. So we still have this idea. Dalton had this kind of billiard ball idea, you know, atom is just this ball, indivisible. And now Thomson has come along and said, but it's got something even smaller called electrons. And those electrons are unevenly scattered within this soup of positive charge. And basically, he called it his plum pudding model. So he imagined having this pudding that was the positive charge, and then the raisins were sort of scattered throughout the plum pudding. And that was his vision of the atom. So we have a little bit more detail now. Okay, then along comes Rutherford. And his proposal was, hey, atoms have this very small, dense, positively charged nucleus in an atom that is mostly empty. So he took, you know, what Thomson had, and he said, well, you know, what about this little soup of positively charged? No, he said, you know what? It's got this thing called a nucleus. And this nucleus is very, very tiny compared to the entire atom. Most of the atom is empty. Now, how did he discover this? Well, basically, they took alpha particles, which are helium ions. They're the helium atom without its electrons. And without their electrons, it has a positive charge. That's what's meant by the little 2+ there. It has a positive charge, these ions. And they were fired at gold foil. Kind of always wondered what gold foil would look like as opposed to aluminum foil. But he fired them at gold foil. And basically, most of them passed right on through the foil like the foil wasn't even there. Okay, and relatively speaking, these are pretty big ions. However, about 1 in 8,000 of the particles were deflected back. So every once in a while. In fact, you know, kind of interestingly, if you noticed in the video on Monday, you know, one of the things they said was, you know, initially they didn't think anything was going on at all. And then he said, hey, did you actually think about some of them might be reflected backwards? Did you check for that? And that's when they figured this out. Basically, he theorized that the deflections were caused by a very dense, positively charged bundle of matter called the nucleus. So you had a positively charged ion, it's going towards the foil. Most of the time it just passes right on through like it's not there, but every once in a while it would encounter that positive nucleus and then bounce back from it. However, because basically 1 in 8,000 of these particles, and the particles are not very big, I mean, you know, they're still definitely microscopic type things. Hey, most of them just went on through. So from that, he determined that the volume of the nucleus must be very small compared to the total volume of the atom. So two big ideas here. One, most of an atom is empty. And two, the nucleus is where all the mass is. So, from his experiments, and here's a little picture of what his experiment looked like. So they had a lead block, they got a radioactive source for their alpha particles, they have the thin gold foil, some screens. You can't see alpha particles with the eye or even a microscope or anything. I mean, they're atomic size, okay? So these alpha particles go right on through most of the time. But every once in a while there would be a deflection, or even one that would come backwards. And so this is basically how his experiment was set up. This is kind of a 2D representation. If you actually see a picture of what he did, it was literally a 3D kind of screen. In other words, the deflection could go in any direction, and the screen was circular so that he could capture whatever happened. As I said, most of the particles pass on through. So from that, atoms have to be mostly empty. Some positive alpha particles, however, deflected or bounce back, and so the nucleus must be positive. So notice how this is carrying on this idea of, something happens, and from what we observe, we can make certain conclusions, and therefore that holds most of the atom's mass. So if you picture an atom, okay, and here comes my alpha particle, and it's just zipping on through, because, again, most of the atom's empty, so just zipping right on through. But then every once in a while, it got close enough to the nucleus that the positive charge would repel another positive charge and deflect it a little bit. Or if it was, maybe head on, kind of like a billiard ball, it would bounce back. And so that was the way they theorized what was going on. Now, this is good and all, but we still got some doubts here about, okay, if that's the nucleus, well, what's going on with those electrons? Remember that kind of plum pudding model? Electrons were part of the atom. Where are they? So one of, I guess you could say, his assistants, Niels Bohr, his work basically looked at the electrons, and he proposed a hydrogen atom model that linked an atom's electron to photon emission. And basically, the way that works is when an atom absorbs some energy, which it can just from shining a light on it, just the way if you were to stand in sunlight, you would absorb some energy from the sun. That can excite an electron, but then when you stop shining the light on it, when you stop pouring energy into the atom, the electron wants to go back to where it was, and so it emits the energy that it absorbed momentarily, and that's what a photon emission is. And from this proposal, he came up with this idea that, hey, the electrons can only circle the nucleus in allowed paths or orbits, kind of like planetary orbits. So in some respects, he had an idea that was compatible with the previous one, in which, hey, most of the atom's empty. If you think of a solar system, most of a solar system is pretty empty. You've got the sun in the center, and you've got these planets in their orbits, but most of the space is empty. And so this is kind of, he was marching along there. He just thought, hey, electrons are in these planetary-like orbits. Now, when in this orbit, the electron has a fixed level of energy, and for hydrogen, the lowest energy state would be in the orbit closest to the nucleus. So he could imagine that there was more than one orbit, if you will, where the electron could exist. The lowest energy one, and he called that the ground state, the lowest energy one would be in the orbit closest to the nucleus, However, if it got excited, it would be in a different orbit further away from the nucleus. Now, as I said, the energy level of the electron is higher when it is in an orbit further from the nucleus. If it gains energy, which is called absorption, it'll move to a higher orbit. And if it loses energy, the photon emission, when it falls back to a lower orbit. So basically, you know, his ideas were matching the energy the electron had to what orbit it was in. And further orbits away from the nucleus, higher energy levels. However, big idea here, the electron can be in one orbit or another, but not in between. So it could kind of jump or fall back, but it wouldn't just orbit anywhere. There were these, that's what I said, kind of like this planetary orbit model. There were these fixed orbits where the electrons could be, but they couldn't be in other places. They couldn't be at in-between energies. Envision a staircase. You can be on one step or another step, but you can't be on in-between steps. Okay, that was the idea that he had there. So, from his model, electrons orbit the nucleus in shells or energy levels. Electrons can be bumped up to a higher shell if hit by an electron or a photon of light. So imagine you've got this electron that's zipping around the nucleus. Nucleus is a positively charged thing. The electrons are negatively charged. So this electron is hit by another electron, let's say. And because of it, it's been bumped up to a higher orbit. So notice that it's a little further away from the nucleus. Now, there are two types of spectra that you can observe when basically you look at hydrogen gas absorption. And one is called a continuous spectra, basically has that kind of rainbow effect. You can see all the colors of the rainbow. And then the other one is called a line spectra. When those electrons fall back, so basically it goes back to the orbit it was in when it emits the energy it absorbed for a short term, they release a photon. And basically those photons come out of the atom and then can be observed as light. Not necessarily visible light, but in many cases also as visible light. These jumps down from shell to shell account for line spectra. And so what you see in the picture there are the absorption and emission spectrums for hydrogen. And you can definitely see from the lower one why it's called a line spectra. You have certain colors of light. And, you know, interestingly, if you were to look at other elements, they would have different lines on them. And so, in fact, you can distinguish one element from another due to its line spectra. By the way, the numbers there, 400 nm and 700 nm. N for nanometer, so that's 10 to the minus 9 meters. So we're talking about very, very small wavelengths there. And then in this case for hydrogen, just a few lines stuck out, and so you can see where they appear. And we will actually do a lab later on where we get to look at the spectra for a couple of different gases. Now, of course, technology and experimentation have come a long way in the last 100 years, and now we have these days something called the quantum mechanical wave model. And basically, we say that it can also be called electron cloud model. The atom has a small positively charged nucleus, so that's still kept. But instead of saying that the electrons are in these planetary-like orbits, now we're saying that there are these regions where we can find the electrons. They're in constant motion, but they are not in these nice circular or elliptical orbits the way a planet would be. They're just in regions, and basically the idea is there are enough electrons to cancel out the positive charge of the nucleus, exactly the same number of electrons as protons, of course, to make the atom neutral. So electrons do not move in these exact path planetary-like orbits, but may be found moving anywhere in a certain region of space related to the electron's energy. Still has that idea that the more energy that it has, the further it will be from the nucleus. But instead of being in this, as I say, elliptical, circular type orbit, now it's more a region of space, somewhere in a certain volume. It is not possible to determine the electron's exact location. Basically, it's a probability thing. A probability will describe where an electron is most likely to be found based on the amount of energy it has. However, as is the case with probability, it does not mean it couldn't be in other places where it's not likely to be found. Now, not very often, but the truth is, we just kind of, later on when we're talking about where electrons actually are for the different energy shells, you'll see that those regions fit into certain spots, but we can't really say 100% of the time that the electron is really always in that one spot. All right, so real quick, we'll just go through the basic subatomic particles. So, one place that Dalton was a little bit off. We do have smaller things than just the atoms. Of course, we have protons, neutrons, and electrons. So protons first, positively charged. Each proton has a mass of 1 atomic mass unit. How do we get the number of protons? We just look at the atomic number. Basically, when you look at any box on the periodic table, you will see two numbers. The larger one is called the atomic mass. The smaller one is called the atomic number. The atomic number also goes in order. So as you go across a row, you see that it goes 11, 12, 13, 14, whereas the atomic mass has a decimal and doesn't go in any particular order except that it generally increases as we go from atom to atom. So, protons. And then, of course, electrons, the negatively charged particles, which are not in the nucleus, but in their electron shells or energy levels. They are very small. They're about 1,800 times smaller than a proton. So mass-wise, we can kind of ignore them as not being significant. How many electrons does an element have? Matches the atomic number. So atomic number, same number of protons, same number of electrons. All those agree. However, because the different energy levels, being different distances from the nucleus, basically have different sizes, bigger sizes as you go away from the nucleus, the shells do not all hold the same number of electrons. The first shell can only hold 2 electrons. The second and third ones can hold up to 8 electrons. The fourth and fifth, 18. And then the last 2 can hold up to 32. Now, if you were to look at your periodic table real quick, you would notice that the top row going across has only 2 elements in it. matching the 2 electrons the first shell can hold. The second and third rows, again going across, can hold 8. There are 8 elements in the second and third rows of the periodic table. Fourth and fifth, we now have 18 that you can count as you go across. Now, it does not look like the last 2 have 32 in them, but those very 2 rows that are at the bottom of the table, below the entire rest of the table, if you look at their atomic numbers, you'll see that they actually fit into rows 6 and 7, and if you were to count them up, you'd get to 32. So if you're ever like forgetting how many electrons go in any particular shell, all you have to do is look at a periodic table, and it matches what row. So first shell, row 1, 2 electrons. Second and third shells, rows 2 and 3, 8 electrons, and so forth. Okay, neutrons, no charge, located in the nucleus. Also basically has an atomic mass unit of 1. Now, technically, a neutron is a proton and an electron fused together. So a neutron is tiny, tiny bit bigger than a proton, but again, since electrons are so small, significant digit-wise, we don't care. So we just say that they're the same, 1 atomic mass unit. Now, this is the only one that you got to do a little bit of thinking to figure out how many neutrons are in an atom. Basically, you have to take the atomic mass number, round it, subtract the atomic number, and then you have how many neutrons you have. You got to have a whole number of neutrons, okay? So atomic mass, subtract atomic number, gives you atomic number of neutrons. So here, 22.99, we can call it 23. 23 minus 11, we have our 12 neutrons. And of course, from this, the mass that an atom has is basically its protons and its neutrons. The electrons are not significant in comparison. Now, let's talk about that mass of an atom, which most cases on the periodic table has a decimal. Well, the reason it has a decimal is because it's a weighted average of the naturally occurring isotopes. Well, what are isotopes? Well, basically, unlike what was proposed many, many years ago, all atoms are not the same for a given element. They can differ. And what they differ by are the number of neutrons that they have. For example, here are 2 forms of carbon. One is called carbon 12, the other one's called carbon 14. Notice that we use their mass number as part of their name. They're both number 6. So they both have 6 protons, and they both have 6 electrons. They match the atomic number. But they do not both have the same number of neutrons. Carbon 12 has 6 neutrons, 12 minus 6. Carbon 14 has 8 neutrons. 14 minus 6 is 8. Now, if you look on the periodic table, it'll say 12.011. Well, where does that 0.011 come from? If you average all of the carbon atoms in the world, basically, 99.9% of them are carbon 12. A very tiny percentage are carbon 14. Enough so that instead of the periodic table reading 12, it reads 12 plus a little bit, 0.011. So there's a tiny percentage of carbon 14. Carbon 14 happens to be radioactive. It disintegrates over about 5,000 years, and so the amount is always decreasing. But when you compare the two and average them, that's where the decimal point comes from on the periodic table. So any of those decimal points you see, basically there are multiple forms called isotopes of that same element, and when you average the 50% of this and 50% of that, that would be easy. But a lot of times it'd be like 60-40 or 70-30 or 99-1, and so you get the different decimal portions. Now, all the atomic masses on the periodic table are based on carbon 12 having a mass that is exactly 12.000. all the other elements are done in proportion to carbon-12. So really, when we say hydrogen has a mass of 1, what we're really saying is it's 1/12 of carbon-12. Because 1/12 of 12 is 1. So, as you will, carbon is used as the standard for all the other elements. They're all done in proportion to carbon. Now, one other little detail here. Atoms are really small, okay? Really, really small. When you look at your periodic table, you are not looking at the mass of one atom. What you're looking at is the mass of 6.02 times 10 to the 23rd atoms, okay? And down at the bottom of the screen, you can see how big that number is. Okay, there's 21 zeros there. It's a huge number. You know, a trillion is 12 zeros. So, you know, we're talking trillion times billion kind of thing. So it takes that many atoms together to get to that 12 grams for carbon. Every mass that you look at on the periodic table is based off of this number. It is called Avogadro's number, or a mole. So all the masses on the periodic table are for what we say 1 mole of that substance. What is that? That's 6.02 times 10 to the 23rd atoms of that substance. So atoms are really, really tiny. It takes a whole bunch of them to add up to anything. Piece of paper you're writing on is about 5 grams. Okay? It takes billions and billions and billions of atoms to add up to something measurable. How do they figure this out? Basically through experiments with gases and a lot of mathematics. But if you wanted to know what was one atom, all you'd have to do is take the mass off the periodic table, divide by that 6.02 number, and you can see for a carbon atom, it is 2 times 10 to the negative 23 grams. So that is 22 zeros after the decimal point before you got to the 2. Very, very tiny. An electron, on the other hand, is 10 to the minus 31 grams. So that kind of gives you a feel for how tiny an electron is, okay? It's another 8 decimal places before you get to the mass of an electron. So atoms, protons, neutrons, electrons, very, very tiny things. It takes a whole bunch to add up to anything. And so, you know, the big thing, of course, is when you're looking at a periodic table and you look at its mass, it's not for one atom, it's for a mole of those atoms, the mole being 6.02 times 10 to the 23rd. All right, so we're going to finish off with Bohr's model of the atom, and you know, a little picture to go with it to kind of demonstrate what things could be. So here we have protons, electrons, and neutrons. Hey, hydrogen, 1 minus 1. No neutrons for hydrogen, not for the normal, everyday kind of hydrogen. So we got that 1 proton in the nucleus, and we got 1 electron in its 1 shell, and so this would be a form of hydrogen. Here would be beryllium. Okay, Bohr model for beryllium. Now beryllium's number 4, so it has 4 protons and 4 electrons. 9 minus 4 would give me 5 neutrons. So in the nucleus would be the 4 protons and the 5 neutrons. And those electrons are in 2 shells. By the way, if you looked on the periodic table, beryllium is in row 2. Well, that first shell can only hold 2, the innermost shell. So that means the other 2 have to be in the second shell. And so you have a picture of the way things are for beryllium. And then here would be an example of aluminum. Aluminum's number 13. 13 protons, 13 electrons, 14 neutrons, 27 minus 13 to give us the 14 neutrons. Now we have 3 shells, aluminum's in row 3, 3 shells worth of electrons, 2 in the first, only 8 in the second. So that gets us to 10. Number 13, we still have 3 left in that third shell. And then a slightly shorthand version of it, you can see on the screen there, where instead of drawing the full circles and putting all those little electrons all over the place, you just have the 2 electrons in the first shell, the 8 electrons in the second, and the 3 in the third, with the number of protons, 13 protons, and 14 neutrons in the nucleus. So a little bit shorthand way of doing a Bohr model for that.